Suppose you type this into a language model. Explain why the sky is blue in one sentence. It may already know all about sunlight and Rayleigh scattering, but a model trained on the open internet has seen many kinds of text that could follow a sentence like this. A direct answer, yes, but also a forum discussion, a list of possible answers, a quotation, even another question. So here is the puzzle. How do you make one of these behaviors become the default without rebuilding everything the model already knows? A useful way to picture pre-training is not as storing one answer to every prompt, but as shaping a landscape of possible continuations. Each stream has some probability. The model already has an answer-shaped stream. It simply has no reason to treat that stream as uniquely privileged. Now, show the model carefully written conversations. Again and again, a user asks for something, and an assistant responds in the desired way. The other streams do not disappear, but probability begins to flow through a more reliable channel. This reshaping is supervised fine-tuning. To see exactly where that pressure comes from, shrink the conversation as far as it can go. The user asks, 2 plus 3? The assistant says 5, and then ends its turn. During a common form of SFT, the user's words are context. They are visible to the model, but they do not contribute to the loss. The gold assistant tokens do. First, given the prompt, make 5 more likely. Then, given the prompt and the correct 5, make the end token more likely. So one demonstration supplies a whole sequence of targets. It teaches what to say, and the equally important skill of knowing when to stop. Give those 2 predictions some concrete numbers. Suppose the model initially gives 5 a 10% chance, and after seeing 5, it gives the end token a 25% chance. The probability of producing both in order is their product, 2.5%. Training measures the surprise of those targets using negative logarithms. Here, the total loss is about 3.69. Now imagine an update raises the probabilities to 60 and 80%. The complete response jumps from a 2.5% chance to 48%, and the loss falls to 0.73. The model has not been handed a symbolic rule. Its shared parameters have simply moved toward this demonstrated continuation, one token at a time. Zoom in, and the update has a simple character. The correct token pulls its probability upward. The competing tokens give up a little probability mass. Back propagation carries that signal through the model. And this is the central surprise. Nothing here requires a new instruction following machine. Pre-training and SFT use essentially the same next token machinery. What changes is the diet. Conversations replace arbitrary documents. Roles become explicit. And the loss is aimed at the assistant's side of the exchange. SFT does not replace next token prediction. It redirects it. This makes a result like LIMAs feel less magical. In that experiment, just 1,000 curated examples produced surprisingly strong assistant behavior in a 65 billion parameter base model. But notice the starting point. The base model was not blank. Pre-training had already built the terrain, language, facts, formats, and many latent task strategies. Each long response supplied many token targets. And because parameters are shared, one update could influence a family of related prompts. The demonstrations did not build a new mountain. They carved a dependable route through terrain that was already there. Powerful, yes. Universal, no. But then how do we make sense of systems trained on hundreds of thousands, or even more than 1 million, supervised examples? There is no contradiction. A small, excellent dataset may expose an assistant interface that is already latent. Reliable math, code, tool use, safety, structured output, and multilingual behavior demand coverage. And the mixture matters as much as the count. Add more math, and math may improve. Remove safety examples, and safety can fall. Repeat one writing style too often, and every answer starts to sound the same. So the dataset is not merely fuel. It is a behavioral specification. How many examples? Is incomplete. The real question is, examples of what? The strength of SFT also reveals its ceiling. A demonstration says, follow this path. But suppose two different paths are both good. The example does not say why one is better. Suppose the demonstrated answer is confidently wrong. Cross-entropy still rewards imitation. Or suppose a much better solution exists, but no teacher ever showed it. These require different kinds of information. Preference learning compares paths. Reinforcement learning with a trustworthy verifier can score where a path ends. There is another wrinkle. During training, the model receives the correct earlier tokens. During generation, it receives its own. One poor choice can change every choice that follows. These are not mysterious flaws. They follow directly from what imitation does and does not tell the model. A modern reasoning pipeline makes this separation unusually vivid. DeepSeek R10 used reinforcement learning without preliminary SFT. It developed strong reasoning behavior, but its answers could be difficult to read and could mix languages. After an initial cold start SFT stage, strict instruction following rose from 46.6 to 71.7. But on AIM 2024, reasoning performance at that checkpoint fell from 77.9 to 59. Pause here, because this is easy to misread. It does not mean SFT generally damages reasoning. It means readable, instruction-compatible behavior and raw verified reasoning can be different objectives. Later reinforcement learning and broader SFT stages recovered and expanded the system. The pipeline kept returning to imitation because discovered behavior still had to be transferred, formatted, and made usable. SFT and reinforcement learning are not rivals. They carry different information. Return to our original prompt. The cloud of possible continuations is still there. Fine-tuning did not delete it. It carved a channel through it, from a user's request toward the kind of response the demonstrations repeatedly rewarded. This works because pre-training has already built a vast landscape of capabilities. And it remains incomplete because a path is only as good as the examples used to carve it. Some regions need broader coverage. Some choices need preferences. Some discoveries need rewards. So the deepest way to think about supervised fine-tuning is not as pouring more information into a model. Pre-training builds the landscape. SFT carves reliable paths through it. And every example is a small, concrete statement about what we are asking the model to become.